amine absorption technologies that are energy intensive are currently used for capture of CO2 from a variety of gaseous mixtures. Potential reduction in the energy consumption is achievable by use of pressure swing adsorption processes that are normally conducted in fixed bed devices. A variety of microporous crystalline adsorbents such as zeolites and metal organic frameworks can be employed in PSA technologies. For post-combustion CO2 capture, 13X zeolite is considered to be the benchmark adsorbent with the ability to meet the US Department of Energy targets for CO2 purity and recovery. The commercially available 13X zeolite is a sodium cation exchange faugisite zeolite with silicon to aluminum ratio of about 1.2. Per unit cell of NaX zeolite, we have 106 atoms of silicon, 86 aluminum, 86 extra framework sodium cations with a silicon to aluminum ratio of 1.23. The extra framework cations are indicated by these blue spheres. The CO2 molecules are these pencil-like molecules shown here. And in this case, the partner molecule is methane. Faugisite zeolite topology consists of cages of approximately 11 angstrom diameter. Each cage is separated from adjacent cages by apertures or windows that are 7.2 angstrom in size. In the process design of PSA units, the Ideal Adsorbed Solution Theory, or IAST, is commonly used to describe mixture adsorption equilibrium. The objective of my presentation today is to highlight non-idealities in mixture adsorption thermodynamics and attendant failure of the IAST. For background to my presentation, consult my paper published in ACS Omega in 2020. Watch also other video presentations on related topics: adsorption versus diffusion in zeolite, the IAST for mixture adsorption equilibrium, and the Real Adsorbed Solution Theory. All these videos can be viewed on my YouTube channel. Let's proceed further by getting a understanding of the requirements and tenets of the IAST. The key tenets of the Ideal Adsorbed Solution Theory are summarized here. All the adsorption sites within the microporous crystalline material are equally accessible to each of the guest molecules, implying a homogeneous distribution of guest adsorbates within the pore landscape. No segregation, congregation, or preferential siting of any of the guest species in the mixture. No change in the specific surface area of each molecule on mixture adsorption. This implies that a guest species occupies the same surface area on the host framework, whether it is present on its own or in the company of partner species. On the basis of these tenets, the partial fugacity of Each of the species I in the bulk fluid phase is written as being equal to the sorption pressure times the mole fraction. This is an expression that is precisely analogous to the Raoult's law for description of vapor-liquid equilibrium. In the event of failure of one or more of these tenets, this expression does not hold any longer, and we need to introduce activity coefficients in this expression to describe deviations from the ideal adsorbed solution theory. The introduction of activity coefficients results in the real adsorbed solution theory. For further description of the theoretical background, I refer you to my publication in ACS Omega in 2021. Watch also my presentations on the IAST and the RAST on my YouTube channel. With this background, let us examine experimental data on CO2 nitrogen mixture adsorption in 13x zeolite. Wilkins and Rajendran published experimental data for adsorption of mixtures of CO2 and nitrogen in 13x zeolite at a total pressure of 97 kilopascal and temperature of 296 Kelvin. The experimental data were obtained for varying amounts of CO2 in the bulk gas mixture. Here is a plot of the experimental data. The component loadings of CO2 are indicated by the red circles. The component loadings of nitrogen are indicated by the blue triangles. The IAST predictions for the component loadings based on unary isotherm data are indicated by the dashed lines. For CO2, the dashed lines are in good agreement with experimental data. However, for nitrogen, the component loadings as measured experimentally are significantly higher than those predicted on the basis of the IAST. The CO2 nitrogen adsorption selectivity is plotted here as a function of the mole fraction of CO2 in the bulk gas mixture. The IAST severely overpredicts the adsorption selectivity of CO2 with respect to nitrogen, and the experimental data are significantly lower. The continuous lines in the graphs here and here are the calculations based on the real adsorbed solution theory. In order to rationalize these results, we conducted configurational-bias Monte Carlo simulations for CO2 nitrogen mixture adsorption under conditions similar but not precisely identical to those in the Wilkins-Rajendran experiments. These CBMC simulation data are available in the ACS Omega publication from 2020 that is cited here. The experimental data, the CBMC simulation data are presented here, and the CBMC data are compared with the calculations of the IAST. As is the case with the Wilkins-Rajendran data, the CBMC simulations also show that the IAST severely overpredicts the adsorption selectivity of CO2 with respect to nitrogen, and we need to introduce activity coefficients in the RAST formulation to capture quantitatively the CBMC data on component loadings and selectivities. A precisely analogous situation holds for adsorption of mixtures of CO2 and methane in NaX zeolite. The CBMC data show that the IAST overestimates the CO2 methane adsorption selectivity to a significant extent. On comparison of CO2 nitrogen with CO2 methane selectivities, we note that the overestimation of the IAST is higher for CO2 nitrogen mixtures than for CO2 methane mixtures. Now, so far what we have achieved is to show that the CBMC simulations are in are in agreement, albeit not entirely quantitatively, with the Wilkins-Rajendran experiments. We need, however, to appreciate the reasons for the failure of the IAST as observed in the two sets of simulations here for CO2 nitrogen mixtures and for CO2 methane mixtures. We shall now demonstrate that the failure of the IAST is due to the inhomogeneous distribution of guest species within 13X zeolite. In particular, we wish to demonstrate that CO2 congregates around the extra framework sodium cations. In order to demonstrate this, we carried out CBMC simulation data to determine the spatial location of guest molecules within the host framework and the intermolecular distances. The radial distribution of guest pairs is plotted against the distance between the guest pairs. The red line is for the CO2-CO2 distances. The blue line is for distances between CO2 and the extra framework cations, and the black line is for distances between CO2 and nitrogen in a CO2 nitrogen mixture at a total pressure of 100 kilopascal, temperature of 300 degree Kelvin. The first peaks are indicative of the segregation or congregation effects for CO2 nitrogen mixtures. We note that the CO2 molecule is closer to the extra framework cation than it is to the nitrogen pair, nitrogen partner. Consequently, nitrogen suffers less severe competition with the CO2 molecule because it is further away from CO2 and CO2 is closer to itself or to the extra framework cation. The same is true for CO2 methane mixtures. The red line is for CO2-CO2 distances in the mixture. This CO2-CO2 is much closer than CO2 methane, and CO2 methane distance is larger than the distance between CO2 and the extra framework's sodium cation. In other words, methane suffers less severe competition due to congregation of CO2 around the sodium cation. In order to drive home this point, we also carried out simulations for CO2 nitrogen mixtures and CO2 methane mixtures in a Fauger with a silicon to aluminum ratio of infinity. In other words, no aluminum atoms and no extra framework cations. In this scenario, we would expect no congregation of CO2 around the cations because there are no cations present. And we note that the intermolecular distances, CO2, nitrogen, and CO2, are all practically the same. An identical situation holds for CO2 methane mixture adsorption in all silica Fauger. The distances between any of the pairs, CO2 pair or CO2 methane pair or methane pair, is practically the same. Introduction of extra framework cations leads to congregation of CO2 around those cations, and for both these mixtures, the partner molecules, nitrogen in this case and methane in this case, have to incur less severe competition with CO2 for mixture adsorption. And this explains the reason that the IAST that presumes or assumes a uniform distribution of adsorbates overestimates the adsorption selectivity. The story so far has been that if there are no extra framework cations, as in all silica Fauger, then there are no congregation or segregation effects. And in sodium zeolite with extra framework cations, the CO2 tends to congregate around the extra framework cations, leading to an inhomogeneous distribution of adsorbates. To emphasize this point even further, we compare the CO2 nitrogen adsorption selectivity for 1585 mixtures in NaX, shown by these red circles, and the blue triangles are for the adsorption selectivity in all silica Fauger. The IAST calculations are shown by the continuous lines. For all silica Fauger, the IAST is an excellent agreement with the CBMC simulated data, whereas for NaX zeolite, the adsorption selectivity is severely overestimated. These simulations are carried out for various bulk fluid phase fugacities plotted on the x-axis. Note also that we're talking now about this is 1 megapascal and this is 10 megapascals. But even at say 100 kilopascal, we see that the IAST estimates are significantly higher by about factor 50 to 100, higher than those from CBMC simulations. Exactly the same scenario holds for CO2 methane adsorption. For 50-50 mixtures, the adsorption selectivity is plotted as a function of the total fluid phase fugacity. We note that the IAST calculations are in excellent agreement with the CBMC data for all silica Fauger containing no extra framework cations, whereas for NaX zeolite with a silicon to aluminum ratio 1.23, the IAST severely overestimates the adsorption selectivity. And we have established already that this overestimation is due to congregation of CO2 around the extra framework cations. So the message that emerges from this presentation so far is that for quantitative calculations of mixture adsorption equilibrium, non-ideality effects need to be considered and incorporated into process design calculations for PSA units. In order to quantify the deviations from the ideal adsorbed solution theory for the four different scenarios highlighted in the foregoing slides, we need to introduce activity coefficients gamma I for each of the guest constituents. The introduction of activity coefficients into this expression results in the theory that is termed the real adsorbed solution theory. The absorption pressures are calculated in precisely the same manner as for the IAST. Indeed, the surface potential and the absorption pressures are the same as for the IAST calculations. The CBMC simulation data could be used to determine the activity coefficients describing deviations from ideality in the adsorbed phase. The activity coefficient for species I is the partial fugacity of species I in the bulk fluid phase divided by the absorption pressure of that species multiplied by the mole fraction of that species in the adsorbed phase. All these three quantities may be determined from the CBMC simulations, allowing the calculation of the activity coefficients. The activity coefficients are then fitted to a model describing the dependence of the activity coefficient on the adsorbed phase composition, x1 and x2. Only one of these is independent because x2 is 1 minus x1. But the activity coefficient is also a function of the surface potential phi. The activity coefficient model may be chosen to be the Wilson model, such as shown here, with two parameters, lambda 1, 2 and lambda 2, 1, along with a parameter c. The parameter c is introduced in order to ensure that the proper limiting characteristics are reflected in the model for the activity coefficient. For vanishingly small values of the surface potential, the activity coefficients of both components must tend to unity, and therefore the parameter c ensures that the limiting behavior is observed. I'll return to this limiting behavior in the next slide. Let's first examine the CBMC simulation data for carbon dioxide nitrogen mixture at a total bulk fugacity of 100 kilopascals and with varying CO2 mole fractions in the bulk gas mixture. The CBMC data are shown by the symbols, and the continuous red and blue lines are the calculations of the RAST using the Wilson model as shown here, and the parameters chosen in the spec are provided here. Lambda 12 is 8.6, lambda 21 is 0.12. Both these are dimensionless, whereas C as the units of kilogram per mole, because phi, the surface potential, has the unit of moles per kilogram. So C times phi is dimensionless. C is positive definite, and this correction factor 1 minus exponential minus C times phi ensures that the limiting behavior is observed. Similarly, the CBMC data for CO2 methane mixtures at 100 kilopascals in NaX zeolite at 300 Kelvin are shown here. The symbols are the CBMC data for the activity coefficients, and the continuous solid lines are the RAST calculations using the Wilson model. The details of these simulations are provided in my paper, ACS Omega 2020. Let's now elaborate on the correction factor here. 1 minus exponential of minus C times phi. We move on to another set of CBMC simulations for carbon-nitrogen mixtures, in which the composition in the bulk phase is maintained constant at the ratio 15 to 85. In other words, the mole fraction of CO2 in the bulk phase is 0.15. These are the data for NaX zeolite at a temperature 300 Kelvin. The activity coefficients of CO2 and nitrogen in the adsorb phase are indicated by the red circles and the blue triangles. And we note that at very, very small bulk phase fugacities, the activity coefficients of both components are unity. Indeed, this must be true because at very, very low pressures, the component loadings in the adsorb phase would follow the IAST calculations accurately. Deviations from IAST will manifest as the pore occupancy increases. The same is true for CO2 methane mixtures, in which the partial fugacities in the bulk fluid phase are maintained to be the same as one another. In other words, the mole fraction of CO2 in the bulk fluid phase is 0.5. We see again that at vanishingly low values of the bulk fugacity, the activity coefficients of both components are tending to unity. And that is the reason we introduce the correction factor 1 minus exponent minus C times phi, because with decreasing bulk phase fugacity, the surface potential also decreases to vanishingly small values, and the value of phi for mixture adsorption calculated from the IAST is the same as that for mixture adsorption using the RAST. These introduction of this correction factor is absolutely vital in order to obtain the right limiting behavior. I explain all of this in my paper in ACS Omega 2021, which you should consult. The reason I'm stressing this is that in the literature on CO2 capture, it is sometimes observed that this correction factor has been ignored. The paper by Shimizu and co-workers, published in Science in 2021, describes the efficacy of a zinc-based Calgary Framework 20, dubbed CAF 20, that is capable of CO2 capture from humid gases. An examination of the experimental data on CO2 capture indicates that strong non-idealities are prevalent in mixture adsorption. The experimental data on CO2 and water adsorption in CAF 20 has been reanalyzed by Harnoon Kaur and Bennett Marshall from ExxonMobil, and the analysis is presented in a paper that is available online. I reproduce here figure 5 of their paper, in which the component loadings of CO2 and water are plotted against the percentage relative humidity. The red circles are the loadings of CO2, and the blue circles are the loadings of water in the mixture. The black circles are the component loadings of pure water as a function of percentage relative humidity. The dashed lines are the loadings predicted by the IAST, and we note that the IAST is unable to provide a quantitative description of mixture adsorption equilibrium. The continuous solid lines are the RAST model calculations using the NRTL model for the activity coefficients. An important point to note is that the model used for the RAST calculations by Kaur and Marshall ignores the 1 minus exponential of minus C times phi correction factor that I explained 2 slides ago. The dotted lines are the RAST calculations with a 1 suffix Margules model. The message I want to put across here is twofold. Firstly, thermodynamic non-idealities are of significant importance for CO2 capture with CAF 20, and great care must be taken in setting up the model for the activity coefficients. And I would venture to say that the correction factor that I introduced a few slides ago, and which I describe in detail in several of my own publications, the correction factor 1 minus exponential of minus C times phi, where phi is the surface potential, must be introduced in order to have the proper limiting behavior, as phi, the surface potential, tends to small values.